So in this video, what I'm going to be doing is exploring the possibility of altering the inertial mass of this disc of bismuth here, which I've weighed to be 194.2 grams. So what this whole apparatus here is something that I've been working on and off for a while, just with trial and error, just trying to get it to work, basically. So far, previous test I've been able to see something happening here. So the basic idea is to create a kind of like fixed oscillation. This electromagnet here controls very precisely the amount of deflection. So with each test I do, I'll know there's going to be an equal amount of energy stored in this pendulum. These are just this is transformer steel. Works pretty well for a type of spring, and so I have it mounted on this plate here with the aluminum tape to reflect away heat and prevent any heat or light or energy going into this material here. And you'll see this is a double-walled plastic material here with an air gap for extra insulation. And this little glass mirror here is just to prevent any convective air currents or whatever that might be possibly influencing this in a way to make errors. So what I'll do here, and here is a Hall sensor with a digital output. And I see it here on the scope here. I get a nice square wave, so it's either on or off. And that makes it easy to measure the decay time. So this was from a previous trial. So you see the decay time here. This is when I excite it here. So it'll do that for, according to this, it'll do that for about 40 seconds before the Hall sensor in here doesn't detect any more movement. And it's also got aluminum tape wrapped around it to reflect away any thermal energy, any infrared or anything like that. So yeah, so what I'm going to do is I'll just do a couple of trials just like this before I do anything to this system, and we'll get a couple of measurements here for total decay time. And then what I'll do is turn this lamp on and do the same thing again. And as this warms up, we will take a couple of more measurements and see what we get here as far as decay time, a change in the amount of time it takes for this system to lose energy or due to retarded acceleration or change in inertial mass. And I also want to add here, I've got this thermometer, which is currently reading 72.1 Fahrenheit. And the sensor is underneath, making contact with the bottom of the plate. And on the back here, you'll see this aluminum tape here, again, to reflect away any incident infrared light, to not heat this up and screw with it. So I will begin here. So we'll see here on the scope as it oscillates. The Hall sensor is switching on and off. And it's set right now for 5 seconds per division. So there's the end. So I'll just stop it right here. Then count that. 5, 10, 15, 20, 25, 30, 35, 40, 45, probably 46 seconds. 47 seconds. I'll try that one more time. So I'm going to try this with a bunch of different materials. Five, 10, 15, 20, 25, 30, 35, 40, 45, 46, 47. Same as last time. Now I will turn the lamp on. So I just want to note that no light from the lamp is shining on the spring system or any of its components, so it's not going to heat that up. Just keep an eye here. Temperature is 74.1. And I feel lots of heat energy, lots of near infrared coming through there. So now it's 86.1 Fahrenheit. So we'll see what this does now. Temperature is now 123.8. We got 40, 5, 10, 15, 20, 25, 30, 35, 40, 45, 46, 47, about the same. Okay, we'll try this again. Temperature is now 136.2. Needs to get pretty hot to see any appreciable difference here. Just going to move that over a little bit. Where are we at? Where are we at? It's 45, 46, 47, 48, almost 49 seconds. Temperature is now off the scale, so it's hot. Let's see if I can get some kind of reading with my infrared thermometer. It is saying 93 Celsius or 205 Fahrenheit. That was 45, was it? 5, 10, 15, 20, 25, 30, 35, 40, 45, about 49. 49 seconds. So just looking at the surface of this aluminum here is 24 degrees Celsius. So it's staying relatively cool. You know what? I bumped that. Sorry. I got to do that again. New start point. So the disc is 100 over 100 degrees Celsius, which is 232 Fahrenheit. Which is only a rough estimate because of the surface is not a perfect black body. Looks like 20, 25, 30, 35, 40, 45, 49. I want to do one more. I hope this proves the point, though. The principle, anyways. That I've discovered. And I just want to give credit to Jeremiah Pop for this particular idea here of having the steel spring arms. He's made his own version of this kind of system, and hopefully he'll be able to share his findings as well. Although he's having a few problems with his setup. All right, almost there. 10, 15, 20, 25, 30, 35, 40, 45, 50. So we're well over 50 now. 55 seconds. That's quite a bit more. Maybe I'll do one more. I don't want this thing getting too hot because it could damage something, melt the plastic, or I don't know. So the power supply here for the electromagnet, I have it set for 1.500 amps. So it's always going to give me the exact same force. Oops, I missed it. I screwed that one up. Okay. 51, 51, 52, almost 53. 53 seconds. Up from, I think it was 47. So the rate of decay of the oscillation has decreased. Now if I touch this, it feels warm, but not too hot. Whereas the bismuth disc, 238 Fahrenheit, 109 Celsius. Let's see if I can get this. So my conclusion is there is a change. I thought it would actually slow down or retard the motion. But what I found from heating metals, brass and the like, that they lose weight, they get a bit lighter. At first I was puzzled by the results of these experiments, but because the decay time has increased to about 55 seconds from 47, that suggests that the inertia has increased, actually. So that would be consistent with my older experiments with the buckets and jugs of water on the horizontal torsion balance, how they seem to slow down under irradiation. Looks like it's going to be about 85 degrees currently. It's been cooling now for a bit, so all right, that's that. And this clip here is just to rule out the idea that the reason for the let's say the easier longer oscillation period is because this being hot heats the air close to it, making it less dense, therefore causing a decrease in drag. So just in case, so there is the idea that this being hot would heat the air, which it does, decreasing the density, the viscosity, so that this can move more easily through hot air versus cool air. But I'm going to do a test where I put this on top here and then heat it up again as before, and then I'll put this over top to eliminate that possibility of air being hot air being a factor to make air resistance less. So we'll give that a try right now. And there's the beginning. So 45, 46, 47, as before when it was cool. Which it is cool to the touch, measuring 22, 23 degrees Celsius. So what I'll do is just cook this for a couple of minutes. And then just put the cup back on, and then we'll do another test. Okay, now up to 75. I'm going to keep this on here. Cup probably won't last very long because it's going to melt. And release. And that's our starting point there. Almost there. The cup is starting to melt. I'm going to have to unplug the lamp. So, yeah, just yeah. So unfortunately, I think we might have made contact here with this. Okay, another trial. Still hot. As soon as I see that cup melting, though, I'm going to turn the lamp off. Yeah. kind of starting to go now. Boom. Okay. 45, 50. There's 50 seconds. 51, 52, 52, 53. So that's still an appreciable increase as before. And I don't think the idea that hot air close to the surface would allow this thing to slip more easily through it, lowering the viscosity. I don't think that's a significant contribution to this. And temperature, it's cooling off now. Still hot. If you'd like to see more videos about this very curious phenomenon, which I think is very important for scientific knowledge and discovery. But if you want to see more of this, want to see me test different materials, just write more in the comments. And be sure you've clicked the notification bell and subscribed to see those future videos. And pretty soon I'd like to put up a few more videos of experiments I did a few weeks ago of, like I mentioned before, weight loss of solids, such as this brass cylinder here under vacuum, how the weight loses a little bit of weight when it's hot, which is very interesting for getting some sort of handle on what can actually modify gravity. And it appears to be temperature related. And now we see it affects inertial mass as well. Okay, thanks for watching.